Testing, testing, 1, 2, 3, testing, testing. Checking the latency. Good. Wonderful. Hello, everybody. Welcome. Oh, I need to get the chat up on my phone. Why do I always forget things? Your prof is a scatterbrain. Doop-de-doo. We'll start at the beginning of the slide set. How's that? Oh, jeez. Should turn the volume down on my phone. Good Lord! Okay, hello. A lot of people asking in the chat if there's a Discord. None that we have set up, and none that thank you. None that we've set up, and none that I am going to probably officially designate or anything like that. I don't know. Maybe I'll talk to the TAs about it and see if the TAs are interested in joining a Discord server. I'm not sure that we want to accept the duty of setting that up or anything like that, but I'm sure at least one of you knows how to set up and manage a Discord. Yeah, I'll talk to the TAs about it. The thing is that I technically have to pay them. Like, communicating with you guys is a thing that they get paid for. Like, that's part of their weekly hours. So, if we have, if we have them split across a whole bunch of different platforms, it might, I just have to keep on top of things like that. But I'll talk to the TAs, see what they say about it. Am I teaching Math 1 MP3? No, I'm teaching Software Engineering 2 MP3. That's the other course I'm teaching this semester. It's a course in C programming, which is a very interesting topic. It's like learning ancient languages. C is a 50-year-old language. Someone already made a Discord. Wonderful. Cool. Well, everybody who likes Discord is welcome to do the Discord thing then. Anyway, so I guess there's some lingering sort of questions about how it is that you should study for the topics in this course. So, just to address these concerns very quickly before we get into the lecture, because, it's the type of thing that everybody wants to know. The textbook is not, it's not a bank from which testable items are going to be drawn. And if I do end up looking through the textbook a little bit to get ideas, the questions themselves will be completely standalone. Your number one reference for studying the sort of knowledge-based requirements with respect to testing will be these lecture slides and my lectures. Excuse me. Secondarily, the tutorials, the stuff that occurs in tutorial is testable, so keep that in mind. You might want to attend them. There was somebody asking in the chat, are the tutorials mandatory? They are not mandatory in the sense that we're not taking attendance, because how the heck would you take attendance in something like this? You'd spend the hour just taking a roll call in the chat. Also, you guys are university students now, and I understand that this is now like I'm used to teaching a first-year class in the second semester when you guys have already had a semester at university to sort of see what it feels like. And I'm really kind of sad that you guys are missing out on the full university experience of like going to these crazy crowded lecture theaters of 500 students and, having the chemistry professor blow stuff up for you right there in the lecture theater. Good times. But, we'll make do with what we have. So, university is a very different sort of set of affairs than high school. We don't come after you to finish your assignments or you finish your coursework. If you don't submit it, you don't get marked for it. It's as simple as that. You know, you guys are now adult human beings, and you got to be responsible for making sure that you get your work in on time. Like, when you're off in the workplace working on, whatever it is that people do in the workplace, your boss isn't gonna come up to you and say, oh, you haven't submitted that thing I asked for 3 weeks ago. Could you please get it in by Friday? No, it'll just be a pink slip. So, yeah, so university is sort of this transitional type affair. You're now an adult. You now get to decide whether the tutorials are worth your time. All I'm saying to you is that I have personally designed the tutorials to be complementary to the stuff that's produced that we're discussing in the lecture. The tutorials themselves are live coding sessions. So I think one of the most useful things that a person can see from someone who knows how to program is to actually watch them program, right? So the tutorials have been designed such that the TA is going to write example programs for you from scratch. The example programs are going to be pushing on the stuff that we cover in lecture. The tutorials are going to be a bit harder than the stuff we cover in lecture because there's that guided aspect of it. The intention is for you guys to be coding along with them. This works usually a lot better in person than it does. It works better in a computer lab than it does online necessarily. But, we're just going to have to adjust to how things work. So, let me... Oh, yeah, so that is... Okay, so a couple of notes about the tutorials. Believe it or not, we are actually still in the process of trying to acquire all of the TAs that we have been, we've been allotted for this course. So, it's kind of terrible. I have this chart that I've been working out to try to determine which TA gets what tutorial, because they have various timing restrictions, etc. So until I have word back from what the schedules look like of the two TAs that we're going to hire, I can't actually assign any particular TA to any particular tutorial. I am, however, doing... this semester I've decided to sort of largely clump together TAs into various roles, and one of the roles that the TAs are going to perform, there's going to be two TAs whose jobs are just doing the tutorials and a couple of other sundry things. One of those is Swale. He's got his I've linked to his YouTube channel on the recommended YouTube channels on my YouTube channel. He's going to be responsible for 3 of them, either the Monday, the Thursday, or the 10 or the 4 o'clock tutorials on Friday. He's going to have 3 out of those 4 tutorials. The rest of them, I don't know. It's possible that I might have to pick up the slack if we can't get people in place in time. So, oh my god, it's been like pulling teeth this semester. It's kind of interesting because, I think it was this class I was mentioning the fact that all of the TAs are undergraduates this semester. The interest, like the thing about that is you guys have very full schedules, so it turns out that actually like getting people in tutorial slots is one of the more difficult things to get set up this. Oh, there's someone in the chat who is like, that's my name! No, don't worry. No, it's Swale Oase is his name. Yeah. And yes, and tutorials are not this week, they will start next week. So don't worry about it. Also, yeah, so if you see a guy called Moonstar in the chat, that's Mark Hutchison. He's one of sorry for outing you, Mark. He's one of our TAs as well, and he is. Yeah, I guess we could scoop some of the previously run tutorials. They're the same tutorial, but it lacks the interactive element, so it's a suboptimal solution. But yeah. Okay. Okay. Anyway, so hopefully that's put some. Oh, I was in the middle of telling you guys how to expect what's going to be on your tests. So, generally speaking, this is kind of an idiosyncratic position, I think, but I'm not a huge fan of multiple choice questions for a programming course. This is a skills-based course. The intention with this course is that you acquire the skill of programming. Programming is not knowledge of abstract concepts. It is the application of skill to problems. I believe that very strongly. So, because of that position, because I believe that to be the case, the assessments in this class are very strongly oriented towards solving programming problems. So, once you get into the assignments, you'll see what I mean when I say a programming problem, but you'll also get an idea of that from the lectures. So, this is word problems, basically. Word problems like you would have had in a high school algebra class. So, for some people this is an elective, for other people this is not an elective. So, because of that, the tests and the exam and all of the assignments are all programming problems. You will be required to write a Python function, typically, in order to solve the problem that you're presented with. In the context of programming, that has a very specific kind of character that we'll get into as we get into this particular lecture. Essentially, the act of programming is the creation of an algorithm. An algorithm is a mechanism for solving a problem. It's like you're putting together a car engine. Car engines have an input and an output, right? The input into a car engine is gasoline and oxygen. The outputs of a car engine are carbon dioxide, water, and forward momentum, or rotational momentum on whatever that engine is powering. So, algorithms function in the same way. Fortunately, they're not quite as complicated as car engines, although sometimes they can be. Yes. Cool. So, yeah, it's Razer Kraken. They're very old, though. They've got, like... I need a new pair. Also, it's like the black faux leather finish on the ear cups is coming off on my head and it getting into my hair now. Well, they weren't that expensive because I got them on sale. Haha! Anyway, so let's talk about programming. We shall talk about an introduction to the introduction to the introduction to programming. We shall talk about algorithms, flowcharts, and programs. So, formulating a problem. What is the square root of 25? You may answer in the chat. Obviously, it's 5. We're not gonna wait for that. What is the square root of some number y? Now we get into algebra. So, the square root of y is some number x such that x times x is equal to y. This is a description of one particular algorithm for finding the x-intercept of some arbitrary function f. This should look familiar from high school algebra. Yes, it's 555. Yes, indeed. So, what is the x-intercept of a function x? Well, first of all, we have to have a definition of what an x-intercept is in order to know if we've found one. So the x-intercept is the value of f, it's the value of x such that f at x is equal to 0. If you take a look at this little graph right here, your x-intercept is right there. So suppose f is a monotonically increasing function on the interval a to b. Monotonically increasing just means that every part of the function, basically, if you have 2 points on the function, say, call them c and d, if c is less than d, then f at c is also less than f at d for all values of c and d. i.e., it's going up, and it never goes down. That's a very mathy way to say that. To determine the x-intercept with precision, epsilon is greater than 0. Generally speaking, the Greek letter epsilon is used to designate error. So within a certain margin of error, epsilon. Step number 1. As long as b minus a is greater than epsilon, do step 2, steps 2 to 4. So, basically, if the interval on which we're looking is already smaller than epsilon, then we have already found the x-intercept within the margin of error epsilon, because either a or b is that x-intercept within the error, right? Generally speaking, you take the average, though. Oh my goodness. My head is doing the brain. Yes, we're going to warm up those brain meats. So, step number 2. Calculate the midpoint, m, which is a plus b divided by 2. If f at m is less than or equal to 0, set a to m. Or, if f at m is greater than or equal to 0, set b to m. So, if we take a look here, in this particular instance, the function is greater than 0. The value of the function at m is greater than 0. So, we can move b over to where m is. This reduces the size of the interval that we're looking on by half. So, in sort of informal terms, the thing that this algorithm is doing is it's closing in on the x-intercept by half each time by looking at whether the midpoint of that is above or below the x-intercept. Man, I wish I had a chalkboard. But yes, what is epsilon? Epsilon is the error, the margin of error. So you can see that this right here is like a mini version of the A to B problem, right? So the reason this algorithm works, however, is that we know that this x-intercept occurs inside of the interval a to b, right? Otherwise, this wouldn't work at all. But you can imagine a scenario if this line came like this way and intersected around here, then at this midpoint, f at m would be below the x-intercept. So you would move a up to where the midpoint is instead of moving b back. So this, yeah, it's very much like a binary search. And binary searches are a thing that we're going to talk about. Yeah, maybe I should use, like, I think you can draw on these things in Adobe. Right now I'm using Event, because, you know, Linux for the win. Anyway, so yeah. So that's a description of an algorithm. We're gonna come back to this and take a look at what it looks like in code a little bit later on. So, declarative versus imperative descriptions. When we program, there are many different types of programming languages that you can use. Generally speaking, some programming languages are good for some things, other languages are good for other things. An intelligent and in-the-know software programmer will know which programming language is good for the application that they're working on and will select the one that's most appropriate. So, programming languages can be divided into two primary categories. You've got declarative and imperative. In declarative languages, you are declaring what something is. In imperative, you are telling the computer how things are done. It's like programming in nouns versus programming in verbs. So in declarative languages, such as Haskell is a good example. Some of you, those of you who are in computer science, will be taking a class in Haskell either now or next semester. I think next semester. But those of you who are not in computer science, you probably will not care very much about Haskell. Haskell's a great language, though. It's one of my favorites. So in a declarative language, you can think of the algebra that you typically do on paper as being a kind of more similar to declarative languages. Rather than telling the computer, okay, assign this memory, perform this operation, move that here, do that with that, what you're doing is you're saying, okay, I want this to be the result. And the computer fills in the gaps for you. Declarative languages tend to be higher level languages. So the declarative side of this is the definition of the problem. We are declaring what the problem is and what the conditions are. Imperative languages are languages in which you provide a sequence of instructions to the computer. This is the older programming languages tend to be imperative languages, and they tend to be a little bit faster and more optimized because they are fundamentally, if you look at the CPU itself, the CPU is designed to be it's designed to take imperative instructions. So if you're programming in a declarative language, those are getting translated into imperative descriptions at some point, and hopefully not by you. So for those of you who wonder how these things apply to the course that we're currently in, imperative languages, Python is an imperative language. Is a declarative language the same as a functional language? That's a good question. So Haskell is a functional language. Functional languages are declarative languages, but not all declarative languages are functional. So it's kind of... and some functional languages mix in elements of imperative languages. They're called multi-paradigm languages. And so, yeah, you could say that functional programming languages are a subset of declarative languages. Some of the other ones are things like logical languages. I believe, technically speaking, some of the weirder ones like HTML might be declarative. I'm pretty sure that HTML is declarative. A lot of people don't even consider it a programming language, though. Yes. So, with respect to our foregoing example algorithm, this is the imperative description of how to perform the algorithm. So declarative is what am I doing? Imperative is how am I doing it? So, let's talk about algorithms. What's the difference between functional and object-oriented programming? That's like asking me what the difference is between a house and a movie. They are completely different things. So they have similar features but not the same? Yes. It's more like functional, saying whether a language is declarative versus imperative, that describes the overall syntax and semantics of the language. It's a paradigm, and there are sub-paradigms. So I should probably define what those terms mean. You'll probably hear me use the terms syntax and semantics quite a lot. I don't think I actually have a slide on the difference between syntax and semantics. Syntax is the grammar of the language. So how you put statements together, what separates statements, whether you've spelled a statement correctly, these are all syntax. What that statement actually means and does inside of the context of the CPU, that is semantics. So the difference between an error in syntax and an error in semantics is that a syntax error is roughly equivalent to a typo when you're writing a document, and a semantic error is your sentence doesn't make any sense. It works grammatically, it just doesn't make any sense. So anyway, yes. An algorithm specifies a sequence of instructions to be executed by a machine when provided with input, and will eventually stop and produce some output. Algorithms do not necessarily stop, but it is preferred when they do. An algorithm that does nothing and just loops infinitely is still technically an algorithm. We just don't consider it to be a very good one because it doesn't do anything useful. So, with respect to algorithms, we've got three main components. We have the inputs, we have the outputs, and we have the instructions. Your task, should you choose to accept it, is to take the inputs, understand what the outputs should be, and write instructions such that you can get from the input to the output. That is a functional description of every single problem in an assignment or a test that we will ask you to perform in this class. So, here are some sort of examples of algorithms that you may know from everyday life. A cookbook recipe. So if you are cooking something and you are using a recipe, you are performing an algorithm. The input to your cooking is ingredients. The output is delicious, delicious foodstuffs. And the instructions are your recipe card or recipe in the book, wherever your recipe is. Sometimes the recipe is just in your brain and you're ad-libbing. It's like, can I put some fennel in this and it tastes good? Let's try it. Boom, it tastes great. Cookbook. Cooking is fun. If you don't know how to cook, you should learn how to cook. Cooking is a lot of fun. Another example is traffic lights. Sometimes you'll be at an intersection and there are these lines that have been cut into the pavement with like a goop filling them in between. These are usually weight sensors that indicate the presence of a car at an intersection. Sometimes, and sometimes it's that and timing, one of the two of those things. These are these weight sensors and a clock can be considered the inputs to what the state of the traffic light is. The instructions would be how to convert weight sensing and the current time that it is into the output signal, which is electrical signals to light bulbs. So, how do you bird water? Well, actually, if you want to get right down technical, most of the time when you get water out of the tap, it has a certain amount of dissolved mineral content, especially if you're living in the country or somewhere else with hard water. So, if you're boiling water and you boil that water dry, the mineral content in the water will stay behind, and it'll sort of get stuck on the inside of your pot. So in that sense, I would consider that to be as close as you could get to burning water. Anyway, so, algorithms. The computation prescribed by an algorithm goes through a sequence of states, starting from the initial state, and each instruction leads you to a new state. This is the state model of algorithms. So, you can consider inputs to an algorithm to be the initial state, and the output to be a final state. When we talk about state, what we're actually talking about is computer memory. We don't necessarily have to get too deep into how memory works in a computer in order to use the computer. That's something that we're going to be getting into in my other class on C programming. But yeah, or proximity sensors. So, what was I saying? Yeah, so when you have an algorithm running, you will very often find it useful to set aside a certain amount of the computer's memory to store intermediate results. In fact, it's not a very complicated algorithm if you don't have to do that. This piece of memory is considered state. That's the term that we use for it. So that's a good term to learn. Another term that you should learn is trace. So a trace is an operation. If you get the computer to tell you what the intermediate states are that your algorithm goes through as it's executing, what's the memory doing while this algorithm is executing, that is called tracing a program. It's a very useful technique for trying to find errors in your programming. But, we'll get into that a little bit more, but trace is a key term. So, where does the term algorithm originate? It originates with a 9th century Persian mathematician. I apologize for my pronunciation. Al-Khwarizmi, I believe. He published a big old book on algorithms back in the 9th century. Man, like that, mid-medieval period, the Islamic world was just kicking ass in terms of scientific advancement. They were really knocking it out of the park, and I believe the term algebra derives from a very similar. Shush you! My goodness, the cat. I believe the term algebra arises from a very similar origin. Yeah, there's a reason that we're all still using Arabic numerals. But anyway, when they translated it into Latin, it sort of became its bastardized Latin version, algorithmi, which eventually became our algorithm in English. So, yeah. Yeah, you can see the cat as if the cat comes within grabbing distance, I will show you Rimby, our kitten. Yeah. Anyway, so algorithms are extremely cool But in order to write a good algorithm, there have to be a couple of... Oh my god. She does this to me in the morning. She'll just come up to me while I'm at my desk and meow at me until I pick her up and rub her belly. But I don't know... she's a black cat, so she blends into the background very easily. Honk. There we go. All right. Say hello to Rimby. Hello. Say hello to the internet cat. Hello. Okay. Now maybe you will give me some peace while I'm trying to give my lecture. So, algorithms are supposed to be executed mechanically. So, the idea of an algorithm is that the algorithm can be performed with no requirement for human input. Once you write the algorithm, you can just set it and forget it. Just like the what was it, the that spit roasting thing that they used to have infomercials on TV for on Sunday mornings. I don't know. Maybe I'm getting too old for. Maybe I'm getting too old. Maybe you guys don't watch television. Anyway, so in order to be executed automatically by a computer, you need two things. First, the algorithm must be precise. Next, it must be effective. So for it to be precise, that means that each possible instruction must be unambiguous. This is not really something that you have to worry about because programming languages are designed so that this is the case. And the algorithm must also be effective. Each instruction must be executable by the underlying machine. Again, this property is provided for us by languages, by programming languages. That being said, with effectiveness, it's a little bit more, there's a bit of a gray area. You may consider a program that never terminates and never reaches the desired output to be ineffective. Like, the algorithm that you're trying to perform cannot be executed by the machine. Therefore, it is an ineffective algorithm. Generally speaking, you should shoot for effective algorithms. Oh my god, are you guys talking about who I look like? My god. Yeah, we're going to get into the issue of compilers. Compilers is like around about here or something. Yeah. There we go. Oh, by the way, so because I made these, I got TAs to make these slides last semester in LaTeX. So these buttons are actually navigation buttons. You can click around inside of the slides with them, which is really cool. LaTeX is, for all of you computer science students, learn how to use LaTeX. It is the document creation system of the future, and also of the past. Anyway. Yeah, Caddy, yeah. So, going back to our computation of the x-intersect problem. Our inputs are what the range is from A to B, the function f that is monotonically increasing on A and B, and you need to know what the precision is, the epsilon. If you know those three things, four things technically, if you consider A and B to be different things, if you know those things, you can perform the algorithm. Without knowing those things, you cannot perform the algorithm. They are the inputs. So, the instructions. As long as b minus a is greater than epsilon, do steps to 4. In terms of programming code, this would be known as a loop because it executes a sequence of instructions iteratively until some condition is reached, and then it stops. Calculate the midpoint. If the midpoint is less than 0, set A to m. Otherwise, if the if the midpoint is greater than or equal to 0, set b to m. The output is some values a and b such that f is less than 0, b is greater than or equal to 0, and b minus a is less than or equal to epsilon. So here's a question for you guys in the chat. Epsilon is error. So, okay, so here's an analogy. In statistics, like if they say on, like if there's an election or something, it's like Justin Trudeau is sitting at 33% of the vote, and Aaron O'Toole is sitting at 31% of the vote, and the margin of error is 5%. That means that any one of those values could be plus or minus 5%. There's a range around that value where the actual value could lie. This is the same idea as epsilon. So, question: what happens if f at m is equal to 0 after instruction 2? So, if we calculate the midpoint, what happens if f at m is equal to 0? Which one of these statements is true? A, the algorithm is not precise because it is ambiguous. B, the algorithm is precise, unambiguous, but the inputs which lead to f at m equaling 0 are not allowed. Or C, in either instructions 3 or 4 are executed. It doesn't matter. Which of these do you believe to be the case? Answer in chat now. Okay. So we got a lot of people saying B and a lot of people saying C. So let's go through it. Let's take C first. Either instruction 3 or 4 is executed. It doesn't matter. So this implies a certain degree of ambiguity. This type of ambiguity doesn't actually exist inside of programming. Notice the term otherwise. So if this is the case, this happens. Otherwise, i.e., if this is not the case, do this test. All right? So in programming code, this is known as what's called an if-else statement. If some condition happens, we do this. If that does not happen, we do something else. So C, not so much. So how about this one? The algorithm is not precise because it is ambiguous. Aside from being a reasonably vague way of saying things, the is this algorithm imprecise? That's a question. Well, for one thing, this is a bit imprecise. If f at m is less than or equal to 0, if f at m is greater than or equal to 0. Both of these include the case where f at m is equal to 0. This is what this one's getting at. But the order of these implies an order of execution. How about B? The algorithm is precise, unambiguous, but the inputs which lead to f at m equaling 0 are not allowed. It's a bit of a trick question, actually. In order to in order to understand why this is the case, we will eventually have to understand floating point representation. If you consider this to be a real number, right? Real in the sense that it's got decimal places. The actual probability of any particular point on a continuous function being precisely equal to some particular value is like infinitesimally small. However, just because the odds of something are very, very low doesn't mean that that can't ever happen. So, the answer is B, and for reasons that we don't know yet. We will be revisiting this example in a few, in like topic 4 or something when we talk about when we talk about data types. Am I centered in the camera correctly? All right. So, question: is the output of this algorithm always unique? What do you guys think? Is it always unique? So we got some people saying no and some people saying yes. Yes, yes, no, yeah, no, 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 no. Lots of people think it's no. A couple of people think it's yes. Person said depends on the input. Ha! There you go. That's the answer. That's the real answer. So, this is a thing about algorithms. Since the instructions don't change, if the inputs are the same, the outputs will be the same. So the output, I'm going to sneeze. Oh my god. Maybe not. Okay. If the inputs are the same, the outputs will be the same. So you're not going to get a unique value every time you run this algorithm, as long as not all of the inputs are unique. So for unique inputs, you get unique outputs. For the same inputs, you get the same outputs. That's how an algorithm works. So, is the output of this algorithm always unique? No. So the no's have it. Boy, the latency isn't bad, actually. So, here are some, one more slide before we break for today. Here are some fundamental questions about algorithms. Number 1. Well, some fundamental concepts related to algorithms. Correctness. In order to determine whether an algorithm is correct, we need to know what the outputs should be for given inputs. This is actually how we are going to use the autograder to grade the assignments and tests that you guys produce. We know what the outputs are supposed to be based on the inputs. We can write software that automatically gives the algorithms that you write specific inputs and test your algorithms to see if they produce the correct outputs. So, that's how it works. And don't worry, we're not going to hide what the outputs should be from you. At least, we're not, like, if we have, it's a mistake. Yeah, it means that the question was imprecise in some way. So, when you get a question, it will usually be formulated in terms of this is the input, this is what we want as the output, write the algorithm. So, software correctness is actually an entire field of study, and my my PhD research. My PhD research is intimately tied up in the idea of the correctness of algorithms. It's a field of study, but the sort of one-word summary is: did you get what you want from the things that you put in? Secondary consideration is efficiency. How long does it take to produce the output for a particular input? We can measure this in terms of time. We can measure this in terms of instructions. We can check this in the worst possible scenario and on average, and of course in the best possible scenario as well. Software efficiency matters. It is actually very possible to write an algorithm that will take longer than the universe is old to terminate, which, is not useful. I'll explain that calculation probably next time. But it's a cool calculation. The other consideration for efficiency is how much of the computer's resources are you using for this particular calculation. So, memory is an obvious one. Memory is finite. You're not allowed to have infinite memory. If you're trying to use infinite memory, you're probably going to end up causing yourself problems. So, efficiency matters. Anyway, let me just check to see if there are any important questions. Will our code be tested for efficiency too, or just correctness? If your code is being tested for efficiency, it will be obvious. It'll say that in the question. There are a few instances in which we will need you to write algorithms for a particular efficiency. However, that is the exception, not the rule. Generally speaking, if your algorithm works in terms of correctness, that is sufficient. There is an implicit requirement that your algorithm is efficient enough to be executed. So if it's not efficient enough to be executed, then you're probably also not going to get any marks for it. However, if it is efficient enough to be executed and it does what it is supposed to do, then it is going to be correct regardless of how you, like the specific algorithm that you put together in order to arrive at it. The purpose of this course is not to inculcate you with one very specific way of programming. In order to become a good programmer, you have to be given the freedom to be able to come up with your own solutions to problems. It's kind of like kung fu. They say a thing they say about when you're doing martial arts is that there are 10,000 students, but only 3 masters. So that is to say, when you're first learning the skill, it's there's going to be a much higher degree of variance among people who are not super good at the skill yet. As you become better at the skill, you'll become more and more similar in the ways that you go about things to people who are good at it and similar to people of your skill level. That's because you eventually arrive at and you approximate more and more efficient methods, and there are fewer efficient methods than inefficient methods. So, anyway, I've probably occupied quite enough of your morning so far. Thank you very much for your time and attention, folks. We will be having our next. I think we're on for Monday. Is it Monday? Blub, blub, blub. Yep. Next. Blub, blub, blub. Words speaking. Our next lecture is Monday morning at 9:30 in the morning. Thank you very much for your time and attention, my good fellow human beings.